In this lecture, I want to talk about a general inference technique called the expectation maximization algorithm. I'm putting it here after k-means, but before we talk about the Gaussian mixture model, because it's something that's used for Gaussian mixture modeling, which is another clustering algorithm. However, it's something that's much more general than Gaussian mixture modeling. It's a very general inference technique for doing maximum likelihood or maximum a posteriori inference. Today we'll focus on maximum likelihood. And also for learning missing data, for learning posterior distributions, approximate conditional posterior distributions of model variables of interest. And today we're going to talk about it mostly in terms of learning missing values of missing data, and also doing maximum likelihood in the case where we have missing data. So to step back, we've discussed a few approaches to data modeling. They've been either probabilistic or non-probabilistic. Examples of probabilistic models that we've discussed include Bayes classifiers, logistic regression, least squares and ridge regression, if we think of maximum likelihood and map interpretations of them, Bayesian linear regression. So all of these models are similar in that we define a probability distribution on some part of the data or the entire data set. So we use probability distributions to define what's a good setting for a model parameter and what's a bad setting for a model parameter. We also discussed some non-probabilistic models. So these are where no probability distributions are to be seen. And as we saw with least squares and ridge regression, sometimes there are connections between the two, depending on your interpretation. But for example, we saw with the Perceptron, there was no probability interpretation at all. Support vector machines, decision trees. In last lecture, we discussed k-means. In all of these algorithms, we had no discussion about probability involved. But in every case, we have some objective function, some math function that we've defined that we're now trying to optimize in some way, either maximize or minimize, in order to learn the model parameters according to how well we can then model the data. And we again saw some different techniques. We saw greedy versus non-greedy ways of optimizing objectives. We saw how with convex optimization we get a global optimal. With non-convex we're only locally optimal. So in every case, though we want to optimize something, there are now different choices that can be made to optimize them and to say what type of optimum we're finding. So that sets the stage for what we're talking about today, one specific instance, where we're trying to optimize a probabilistic objective function called maximum likelihood. So in the most basic scenario that we're going to work with today, we have this setup. We have some set of model parameters, theta. These are the parameters of our model. These parameters define a probability distribution on data, and we want to learn them. We also have a set of data, x1 through xn. We have a probability distribution that we define on the data, the probability of x, the data x, given the model parameters theta. And we're also going to make an assumption in this lecture of independence and identically distributed data, IID. So what this means is that each observation is generated IID from this distribution. Conditioned on theta, all the data are independent and they have the same distribution. Now, if we want to find a setting for the parameter set theta, we can use maximum likelihood. And what this approach does is it tries to find the value of theta that maximizes the likelihood of all of the data. So we have a probability distribution on our data set. Depending on what we set theta to be, that will change the probability of the data set that we observe. So these are fixed values that we plug in, and now we maximize this thing over theta to find the setting of the model parameters that best explains the data that we see. And we can write this a few ways, this optimization a few ways. we see how if we have an IID assumption, that this likelihood factorizes into a product over individual likelihoods on each data point. And finally, because we want to find the point theta that maximizes this likelihood, we can also find the point that maximizes the log of the likelihood. And that's because if one probability is greater than another probability, then the log of the first probability is greater than the log of the second probability. So maximizing one is equivalent to maximizing the other. And that helps us to make this easier to work with in practice, where we have the log of a product is now the sum of the log of each of the individual terms. This is the final form of what we're trying to maximize in theta, and it's much easier to work with. We've already discussed maximum likelihood for a few models. For example, least squares linear regression, if we view it as a Gaussian likelihood, and also the Bayes classifier. We saw how that was an instance of maximum likelihood. Both of these models were nice in that we could find their respective maximum likelihood parameter settings in closed form by simply taking derivatives, setting to 0, and solving an equation. And out of that, we would get some equation for the maximum likelihood parameter, where we simply plug in our data and evaluate to solve for the parameter. Another example that we saw in the first lecture was this very simple model, where if we assume that our data x is generated IID from a Gaussian with a mean mu and a covariance sigma, then if we find the maximum likelihood of those parameters, the maximum likelihood value for the mean is simply the average of all of the data, and the maximum likelihood for the covariance is simply the empirical covariance of the data. So here we just empirically calculate the covariance of our data, and we set the covariance matrix to be equal to that. Now, in more complex models, we might want to split the parameters into groups and do coordinate ascent. So we saw this with k-means, where we called it coordinate descent, because we wanted to minimize that objective function. With probability functions, we're always trying to maximize something because it's a probability term, and so we want to find the most probable thing. So we want to always maximize something. So in this case, with a more complex model, we might say take our parameters theta and split them into two different groups, theta 1 and theta 2, and then maximize the likelihood over both of these things. So maximize the log of the likelihood over theta 1 and theta 2. However, we can't do it analytically. So this is, we're speaking in abstract terms here. We imagine that we can't do this at the same time, because we can't take the derivative of both of theta 1 and theta 2 and optimize them together. However, given one value, we can optimize the other. So this would lead to a probabilistic version of coordinate ascent. So we would have something that looks like this. If we're trying to maximize an objective function that looks like this, log of the likelihood, for a particular iteration t, we might take the value of theta 2 and fix it at its value at iteration t minus 1, and then maximize this thing over theta 1 only, holding theta 2 fixed to its previous value. And that might be something we can do very easily in closed form, for example, with an equation. And then given this update for theta 1, we plug that value in for theta 1. And now we maximize this thing over theta 2, holding theta 1 fixed. And again, that often is something that we could do in closed form by taking a derivative, setting to 0, and solving. And so we iterate back and forth between updating theta 1, holding theta 2 fixed, and then updating theta 2, holding theta 1 fixed. And eventually we converge to either a global optimal or more likely a local optimal solution if this is non-convexed. Okay, so this is all in the way of setting the stage for the EM algorithm. So there's a third subtly different situation where we might really want to find the maximum of this log likelihood over theta 1, where theta 1 is the only parameter that we have in this function. However, it's for some reason tricky to maximize this. Maybe it involves gradient methods that don't have stable gradients, or for some reason it's tricky. However, we figured out that we can add a second variable, theta 2, to the model, such that the maximization of this thing over theta 1 and theta 2, for example, through a coordinate ascent algorithm, is easier to work with. So this often is the case. This is not necessarily going to be clear right yet exactly where we're going, but we're going to take this idea. This observation forms the foundation for what we're going to discuss next.